Welcome back to my Commodore 64 Games Memories video series. This is where I look at old games and some of the technical details behind them. Today we have Spindizzy, published in 1986 by Electric Dreams. The creator was Paul Shirley. I remember back in the day being very impressed by the graphics in this game, especially the variation in the backgrounds and the large number of levels. So we're going to be looking at this today. This game was suggested by one of the followers of my channel, and I'm always happy to take suggestions for games to have a look at. So yes, if you like these kind of technical deep dive videos, then please do consider liking or subscribing to this channel, or sending me a super thanks. They are all always very much appreciated. Using C64 Debug GUI, we can see the title screen of the game. If we switch into the VIC debugging view here, we can see that the game mode is actually just using a multicolor bitmap mode. There's no screen split or anything like that. On the title screen itself, there's no sprites active at all. We can see that the targeting cursor shows that the screen is basically consistent all the way down using the raster beam targeting cursor, so we know that it's just a multicolor bitmap screen. Going into the game, we get this rather lovely 3D view. We have this rather lovely sprite being used for the controllable player vehicle thing, or whatever it is that you're meant to be using. It's meant to be some kind of like survey drone or something, isn't it? You're meant to collect these crystals anyway. You can see that redrawing the screen between each room seems to draw from top to bottom. Now, you'll notice that the player sprite here, the multicolored version of the player sprite, is slightly masked out by the pillar, which is on the left-hand side. You see the player sprite is, well, yeah, the player drone is behind. But if I make this other sprite, there we go, I force it to be white, we can see that actually the player sprite is made up of two sprites, a high resolution overlay with the multicolor sprite data underneath as an underlay. And I think this is what makes the player sprite graphics look so interesting, is that it's using a high resolution overlay. In this screen, which is eastwards from the starting area, we can see that the lift sprites and also the player sprites are being masked by the level above, but also as the player sprite changes its screen position with respect to the lift sprite, actually the lift sprite and the player sprites change, and that's because on the Commodore 64 the sprites have priority. So there's a priority between sprites 0 to 7. So if you want sprite 0 to appear in front of, if you want the player sprite to appear in front of the lift sprite or vice versa, then you change where the player sprite is rendered, or which sprite is rendering the player sprite and which sprites are rendering the lift sprites. And then the Commodore 64's VIC chip sprite video capability will render correctly with the correct priority. So that's why you can see from the VIC debugging view that the lift sprites and the player sprite graphics are swapping over when I move the player sprite around the playing area, and that's because you want the player sprite to appear in front or behind of the lift sprite. But also the lift sprite graphics data there, you can see it's getting masked by the level above. And then if I move the player character around, there we go, you could see that the player sprite and the lift sprites, they changed order in the VIC debugging register view there. The C64 Debug GUI there is great for showing red bounding boxes around where the sprites are. We can see that the player sprites are completely masked out. We have this rather lovely map view as well in the game, which shows you where you are in terms of the large level map, which is always very helpful. The more you try and use your speed by speeding up the player controlled device, or if you use the brakes by pressing the spacebar, or if you increase your speed by pressing the fire button and moving around, I think it uses up time. If you collide with other enemies, or I think if you die, your time also decreases. Let's move into the other screen. There we go. If I get hit, then my time in the top left-hand corner decreases rapidly, and then your time decreases to 0, and then you have a mission aborted, and then you go back to the title screen. That's your game over. So we can see that the enemies that were wandering around the screen as well, they were also using sprites. This is the memory debug view in C64 Debugger. I'm just looking at the start of memory, so the 0 page memory locations, plus a little bit of the stack at 100 in hex there. I'm just looking to see if I can find what's going on now. If I look at the memory view here, look, this area, whenever if I press the function keys, it changes between north, south, east, and west views of the level screen. But I could see in the memory view that it was doing quite a lot of processing in the middle of RAM when I was redrawing the view. So the bitmap screen obviously needs quite a lot of memory updates to redraw the new screen. But once the screen is drawn, then it doesn't need that many updates in the bitmap itself. But the level data, there seemed to be some pre-calculation of level data going on in the memory view. Let's make the memory view a lot larger so we can see what's going on now. Look, that particular view there, when I change level, you can see that there's a lot of processing going on there. And this level data looks almost like it's containing something to do with what's visible on the screen, right? The data pattern visible in that block of memory seems to represent a version of the map or the screen which is visible when you move between the screens, the map screens. So that's going to need more investigation, I think. There's a lot of writes going on, there's a lot of reads going on, and then when the bitmap at the bottom is drawn, that corresponds to lots of data being read from that memory area, and then lots of writes going into the end of memory bitmap data. I've just noticed that these 0 page memory locations here seem to represent the time in low byte, high byte format. So the time is now 184 in hex. Oh, sorry, 184, 183 now in decimal. But it seems to be binary coded decimal in those memory locations there in 0 page. So that's 5E and 5F, the game time low and high. That's going to be really useful because when we're debugging this game, we want to have infinite time. We don't want to have the timer countdown. So when we're debugging this, probably in ICU 64, then we're going to make use of that. So we need to find the code which updates those two memory locations. But at the moment, we can update the debugging notes text file, which of course I will be committing to source control, my GitHub repository, and I will put a link to this debugging notes text file in my video description below, so you can follow along with the notes that I've been creating as well, if you want to do so when you're watching the video. So we found out so far that we have high res over multicolored sprites for the player. We can see that the sprites are masked, and I could see that the sprites had like an 8 pixel horizontal resolution for the sprite data, but the vertical resolution was at a pixel resolution. And that's probably because it just makes the masking routine simpler. It means actually that the player sprite is 16 pixels wide, I think, right? Yeah, and because you need to have a spare 8 pixels on the side because it's reduced the horizontal pixel resolution for the sprite position accuracy anyway. But yeah, I think that just makes the masking routine a lot easier. Basically, the sprite data would shift left and right in pixel jumps, and then the sprite itself would shift left or right horizontally in 8 pixel jumps. So the sprite data was reflecting the pixel accuracy. This large blob of calculated memory data between the map when transitioning between the map screens seems to start at AA80. So we're going to have a lot deeper view into this memory block here at AA80. It's quite a large memory block. you can see most of the time is actually filled with FF, but we'll investigate that further when we're looking at the code disassembly in ICU64, I think. But it seems to be an off-screen buffer that's used where it has data calculated into it before the bitmap screen is finally rendered and updated. So there seems to be quite a lot of pre-calculation going on, and that's not a surprise, right? It's pretty obvious that this game is maintaining some kind of depth buffer information because it needs to mask out the sprites, but also there's quite a lot of pre-calculation going on before it does a top to bottom render or onto the bitmap, and it's only using a single buffer bitmap as well. So because there's no double buffering going on, you can actually see the bitmap being rendered from top to bottom. So that implies that there's quite a lot of off-screen calculation going on. When the player sprites were moving around, this memory area at AA80 onwards, this large pre-calculated memory buffer, the player character is reading from that as well, and that's for the sprite masking, I'm pretty sure of it, but we'll delve into that. So on the first screen, on the default screen that you start the game on, when the player character is in its default middle of the screen position, then these memory locations here, B1, B9, B1, BB, B1, BC, B1, BD, are all being read, as well as B2, B9, B2, BB, B2, BC, B2, BD. We'll look at these in more detail, but I did notice that if I change these values here, these specific values, then I can alter how the sprite is masking out. It's actually causing the player sprite to be partially masked out, as if there was a block in front. So these particular values, I think they seem to be like maybe Z values or something like that. Maybe I'm effectively pushing these blocks, which are meant to be behind the player character, to be kind of like tricking the game that they're actually in front of the player character, because the player character is going to have a depth as a function of its vertical Y position on the screen, right? There's a direct correlation, I think, between the depth and the vertical Y position on the screen, pretty much. Well, it depends on how high the player character is above the ground, of course, but there's a plane in front, if you like. There's a vertical plane, and the Z position is going to change roughly further up the screen the player character is. But if I tweak these values in memory, then I can cause the player sprite to be masked out. So I think you need to have a little bit more look at this in a property bugger. If I tweak the other adjacent values in memory in this large pre-calculated buffer, I can change the shape of the mask which the player sprite is masked out by. So changing these values here, which are not the Z values, I've already changed the Z value to 44 at B1C1, so it's quite close to the camera in effect, I guess. But these values before what I think is the Z value, or what appears to be the Z value, if you like, the Z buffer value, these values here, if I change these numbers, then it seems to change how it changes the shape of the mask which is being taken out of the player sprite. So yeah, this definitely needs more investigation, I think. And this is what debugging looks like. It's a lot of empirical testing usually. So I'm just updating my debugging notes text file here about the findings that I've made so far about this block of memory. But obviously the understanding is it's a first pass. So there needs to be a lot more detailed investigation going on here to be able to understand properly how this game works and how it renders this view. So here we are in ICU C64, which is Vice plus all of these extra debugging windows. Let's do a watch store for 5E and 5F, which were the memory locations that contained the time. Okay, here we go. We've triggered on this particular piece of code here. It seems to be GSR to 9BCA. Then there's a set interrupt and a set decimal instruction, SED. Oh, well, that's funny. It means that it's stopping the interrupts and it's setting the decimal flag. it's postponing the interrupt, really. If an interrupt happens while the interrupts are disabled, it will just queue the interrupt until after the interrupts are re-enabled again by clearing the interrupt flag. But the SED is interesting. It means that it's setting decimal mode, which makes sense because those two memory locations, 5E and 5F, contain binary coded decimal. And so we expect the set decimal flag to be set because it's doing an add with carry and then a store back again. This does look like it's slightly obfuscating how 5E and 5F were being updated, because the add with carry, comma x, add with and the store into 0, 1, comma x, that's kind of like slightly obfuscated loading and storing of these two memory locations. This code is only called from two different places as well. I just did a hunt for 220, and the start address of the memory of the routine for doing this update, and we can see that it's only doing this 20CA9B opcode sequence in two different places, and that means that it's just updating 5E and then it's updating 5F with this routine here. So yeah, I'm pretty sure that this is the routine that we don't want to run if we want to disable the timer counting down or just the timer being updated. Just before I modify the routine, which modifies the timer 0 page memory locations, I'm going to see if there's any loads going on for the bytes that I'm going to change to an RTS. And in this quick superficial run through the game, I'm going to go through some screens. There doesn't seem like there's any code which loads from the beginning of that code in memory. So I'm thinking at this particular point in time that it's going to be safe to change the beginning of the routine to 60, which is an opcode RTS, which is returned from subroutine. So instead of this routine doing something, the routine's just going to RTS straight away. It's not going to do anything at all apart from return from its subroutine. And then we'll see if the timer is now suspended or disabled. So yeah, going back into the game, I'm holding down space just to see if I can run down the timer. It doesn't. Usually space, when you press the brakes or use the brakes by pressing the space bar, the timer will decrease rapidly. So I think we can save the game now as a snapshot in ICU64, well, Vice 64 anyway, as a snapshot file, so that I don't need to remake or redo those code changes to disable the timer. So now we've got a disabled timer, we can go back and have a look at what looks like this pre-calculated Z buffer with other masking data built into it. Okay, so now we can experiment properly. We're not going to encounter a decreasing timer. So let's get to that memory location that we noted before. All of this is code. The memory location that I'm looking for, not those ones. Let's keep on going. It's these ones. There we go. All of these are the reads from that pre-calculated memory buffer. I'm just looking for the player character reads. We've got two sprites, you see, on the screen. We've got the player character reads, and then we've got the reads going on for the lift, which at the moment the lift is not moving, it's stationary, but if I hit that switch underneath the lift will start moving up and down. Anyway, so now we can start experimenting with these memory locations. Now, because the code is consistently reading these memory locations, we know that we can tweak them, and then we should see stuff happen in the game, right? Just looking through the memory here, I can see that there's 1, 2, 3, 4 copies currently of the sprites which are visible on the screen. That seems to be like a sprite cache. If I move to this screen here, then we can see actually that we've got a whole bunch of extra sprites being calculated all the time. And these are all different frames being used by the game. So anyway, let's go back to that snapshot, see what we can find when we experiment. We can see the graphics as well. So when the sprite graphics frames, when they get calculated and when they get masked out, we'll be able to see that in the graphics map debug view. There's some other extra bitmap data there at the beginning of the last Vic back there at C000. There's that large memory block there which is being calculated into as well. But we seem to have what looks like some character set information for the level data itself, and maybe what looks like some masking information as well. That might be interesting to look at. So let's change the apparent Z value, and the lift has had its top left-hand corner masked out. So if I change it back to 4C, you can see that the lift returns back to normal, and those other adjacent memory locations are not being read. But if I change this second value here, which was 28 to 4D, when I change it to 4D, it causes the left and right memory locations to start being read again, which is weird. If I change it to 1, if I change it to 0, okay, if I change it to 1 again, okay, if I change it to 2, what happens on the screen? Nothing is there. If I change it to 3, nothing is happening there either. I'm looking at the lift. Wow, okay, so the lift has changed. The mask, it's showing a different masked cutout of the sprite data. Look in the graphics map view there, it's a lot easier to see than looking at the rendered Commodore 64 screen. If you look at the graphics map data for the sprite frames, the cutout, the masked out area for the lift graphics data changes when I change these numbers here. These cutout shapes seem to correspond to shapes of the tiles that are commonly used in the game view. So there's a few different diagonal shapes, and there's like a corner shape and stuff like that. This is interesting. It's not entirely unsurprising, you know. The sprite data needs to get masked out with the apparent shape of the bricks that are going to be in front of it. So I'm not really that surprised that this kind of data change is causing that to happen. So I did notice that this routine here, which is accessing the memory, is loading from C300, ANDing it with B900, and then storing it with C300. And that's loading data from 953C. 953C seems to be some kind of like source data for maybe the graphics data, and then it's doing an AND with what looks like masked data, so basically corners of blocks and stuff like that, and then storing back into the calculated data for the sprite definition. I think that's what this code is doing. But it's basically doing a load with graphical data, ANDing it with a mask, and then storing it back out again. And that corresponds to reading like a shape definition from this pre-calculated buffer, which seems to also include a Z value as well. So each 2x1 character block on the screen, when I say character block, I mean the character block cells of the bitmap screen. Each 2x1, so 2 character blocks horizontally and 1 character block vertically, on this bitmap screen itself seems to have or be represented by 8 bytes in this pre-calculated buffer, and the pre-calculated buffer seems to have a shape or mask shape index and then a Z value, and it has 4 of those pairs for each 2x1 pixel block. And it seems to be, when I was experimenting with the memory view, it seems to have like a far to near Z value, so that if the player character is greater than one of the, or 2 or 3 or 4 of those Z values, it seems to accumulate different masked corners of blocks that could be in front. So that means that there's kind of like a depth complexity to these levels, and the shape of the final mask for the sprites that should be behind it, or should be behind a certain position, will be updated by a combination of different corners and different slopes and gradients and everything else that could be corresponding to the characters in front of it, which is rather an interesting way of doing it. So if the sprite obscuring or masking code is using this data, my next thought is what is calculating into that mask and depth buffer area of memory, right? Because that's going to be the real interesting part. How does the game store its screens in this very, very large map? I mean, there are tons of screens in this game, and there's huge bitmap screen at the end of memory, and there's all of this pre-calculated currently visible level data buffer, depth buffer plus mask information there, right, in memory. So, and there's quite a lot of code too. So where are all of the game's map screens, and how is the map data? What does the map data format look like? I think that's what we need to look at next. What calculates into this depth and mask buffer here? So let's do a watch store for B148, which is that memory location that we know the player character is reading. So we're not doing a watch on the read, we're looking for a watch on the store. So what's that doing? So this looks like it's 975B, the routine at 975B looks like it's filling the whole buffer with FF. Okay, that's reinitializing the whole buffer with FF. FF being, I think, a Z value which is, I think, closest to the camera. A value of 0 is furthest from the camera, right? Because when I made the values larger, it pushed a mask from behind the player to in front of the player. So yeah, that makes sense. So filling with FF means that it's just initializing the whole buffer with FF, and basically a Z value. And it doesn't really care what the mask information is, because the Z value is just being cleared to FF, which is closest to the camera. The player is never going to reach that position, so that's okay. So the test won't actually pick out the corresponding mask byte. Okay, cool. So this routine clears that first. We need to look for what is storing into that cleared buffer now. So let's have another breakpoint at B148. There we go. The memory debug information flashes yellow, and now, yep, okay, so there's this code here which is trapped on a store, and so this routine here, which is not the clear routine, is actually storing information into this mask and depth or Z buffer area of memory. There seems to be quite a lot of quite relatively complicated calculation going on. So stepping back a little bit, the buffer is cleared again, but then after the buffer is cleared, then we get to this routine here. After the mask and depth buffer is cleared, it seems to be initializing some zero-page memory locations to point to B700. Okay, and also, well, an 8x8 grid. 1, 2, 3, 4, 5, 6, 7, 8. Okay. FB and FA, FA and FD seem to be memory locations in zero page, which are initialized to 8 and 8. Oh, and 8 as well, so maybe it's an 8x8x8 grid. Okay. Ah, well, look at that. Memory location B700 seems to have 4 1 filled in, and then 7 0 bytes. And it seems to be doing that for an 8x8x8 grid, which corresponds to the game grid that we're seeing on the screen. So maybe, I think the mask and depth buffer, the calculations that are going into the mask and depth buffer seem to be coming from an initial what looks like an 8x8x8 grid area, which is coming from B700 memory location, where there's another data table. Oh gosh, okay, so we need to try and understand what stores into B700 as a memory block now. So I have an idea. After B700 data table has been calculated into, but before the mask data and the Z buffer data has been calculated, let's put in some more 401 values into this table memory range at B700 to B8FF. Okay, and now let's oh, look at that. We can inject blocks into the game screen. So yeah, the memory location or the memory block at B700 to B8FF, so an 8 by 8 by 8 grid, will allow us to inject blocks into the currently rendered screen. Well, that's quite cool, isn't it? Okay, so we can use that information. We can now see. We will now have to see what calculates block data into the B700 range. Okay, so that's okay. So the B700 data table is definitely B700 to B8FF. It's only clearing those two 256 byte pages, or 200 bytes in total in hex, and that makes sense, right? Because that's what we would expect from a an 8 by 8 by 8 grid of block bytes, because 8 by 8 is 64, and then times 8 again is 512. Yeah, 64 times 8 is 128 times 4, which is 256 times 2, which is 512. Yes. So let's do a ranged breakpoint for this grid data area, which is the 8 by 8 by 8 block grid. And we can see that it's doing a store here at indirected FA, Y, which is a stop on store at B700. Okay, so it's storing into the first block, into this, we'll call it the grid space, the grid level space, or the level grid space, I think, because it's an 8 by 8 by 8 grid of what looks like block values. So this code here seems to be doing something interesting into this memory table. So this code here seems to be calculating into the grid, level grid data. The level grid data is then used to calculate into the mask and depth data, and the mask and depth data is then used for the final bitmap rendering pass. So there's quite a lot of pre-calculation going on in this game before it actually renders into the bitmap. In the memory map view here, we can see that it's a 4-1 followed by 7 zeros. If I change this to all be 4 1s at the beginning of the level grid memory block here, and then let the game continue on its rendering. Okay, so let's continue on. Okay, and there we go. We have a vertical stack of blocks. So yeah, I think we can safely say that we have 8 values for those 8 blocks which are stacked vertically. So we can see that the vertical height is the first 8 bytes of this memory block range, and then so we have 8 bytes for the higher blocks, and then we have the next 8 bytes for the next vertical column, which goes down the level grid. So the data is oriented that way, which kind of makes sense. You want all of the blocks or tiles at a specific coordinate to be oriented vertically. Okay, I think it makes sense when you're doing calculation from a point of view of just updating like the X or Y index register to read the next highest block in a particular column. Anyway, I think that makes sense from a code optimization point of view. But what does this code do here? We need to really analyze what this code is doing. It seems to be, when I'm stepping through this code, it seems to be doing quite a lot of calculation when it's drawing block data into this grid, level grid map. So this code does an awful lot of reading of data and then looping around. I mean, is the map data or screen data run length encoded data? Maybe, or some other kind of like compression scheme? So I did notice that when I step out to the previous routine, which is storing data into the level grid memory range, I noticed that it's doing some loads in 3-byte chunks for every new block that it's adding to the level grid data. So it's reading in 3-byte chunks from this memory range here at the moment. So if I advance with the next breakpoint, then there's another 3-byte green memory read chunk going on there. So it seems to be reading in 3 bytes and then storing tile data into the level grid memory block. So when debugging this even more, I did notice that FA and FB and 0 page contain like the screen coordinates, right, which is 4040 for the default screen at the start of the game. This code here seems to start scanning from A00 and scanning through that level data, I think it's level data, until it finds a matching coordinate. And if it doesn't find a matching coordinate, it seems to skip over a number of bytes, and I think that's a variable number of bytes per screen, which makes sense because some screens are complicated and some screens are not. But when it finds a matching coordinate, it takes that memory address for the matching coordinate for that block of data, which I think is the screen level data, and then it starts processing that. So the default screen at the beginning of the game seems to start at 1023. So I'm pretty sure that 1023 is the default screen at the start of the game, the level data for that. So let's put a watch load on 1026, which stops the monitor, machine code monitor, when memory location 1026 is read. That's 3 bytes after the start of what I think is the beginning of the level data, after the map coordinates have been matched. So there's 3 bytes, X and the Y coordinate if you like, and then the size of the data for this particular screen. So we can see that this code here, I'm going to trace through the code and I'm going to note down what I think the code is trying to do with these bytes which is loading in, because I need to try and spot patterns in this level data, or what I think is level data. I mean, this level data seems to store things into the pre-calculated level grid, which is the 8x8x8 grid of data, before it even gets to the mask and the depth buffer. Depth buffer. Yes, there we go. I need more coffee. Anyway, so memory address 1026. And then let's create a little table of observations, right? So we're going to empirically test this. The initial starting value is 1, 2 at that memory range. It's doing an AND with 1, 0 anyway. Okay, and it's doing a branch not equal. Okay, so that tells us initially that there's some kind of like flag, perhaps. This is the code which accesses that particular byte for the start of this default screen level data. I'm hoping it's level data. It looks like it's level data, but we'll just keep on plowing through this, gonna have to be very methodical in this because this routine looks like it's quite difficult to understand. So because there was an AND with 1, 0, we're going to say, I think that, or we're going to highlight that maybe there's a flag of 1, 0. We don't know what it does yet, but we can try and test that by tweaking the memory values in a bit. Maybe it's a block type, perhaps. I don't know. We'll just note down these assumptions and we'll see what happens. The F was a mask value for the lower 4 bits. So each level screen does change color, so maybe it's a color value, and that, so we'll change that, and then maybe this next byte along is the block type. I'm just putting some guesses down here based on what I'm reading in the code, because it's loading the next byte value and storing it into F8. It's loading the next byte value after that, and it's storing it into F9. F9, I think, when I was looking at this routine just now, F9 seems to be the height. Okay, so we'll put a little comment in there saying height question mark. So that's the next. So that's the third byte that it's used, that is read. Okay, so let's just change the second byte to be a 2, right? And then press F1 and cause the screen to redraw, because look, it's changed the block being used. Let's change it to 3. Yeah, it's changed the block type again. Okay, let's change it to 1 again and change it back to how it was. Let's change that third byte to be 1 now. Oh, look. It's raised up the bottom. Let's change it to 2. Yeah, look, it's raised up the whole plane. Okay, that's fine. Oh, okay. Okay, so that basically is right. It is the third byte is the height. Okay. If I change that to be 3, then there we go. At the moment, the player character is falling through the bottom of the level, so it's constantly redrawing anyway. So when I change these values around, there we go, it's redrawn the screen. That's quite funny, isn't it? And the timer is disabled as well. So let's change this to be 1, 1. What do we get? And then let's press F1 to redraw the screen. Oh, look, the color of the game screen has now changed. Interesting. Let's change it to be 1, 3. Oh, look, it's changed the color of the screen. Okay, so the lower 4 bits maybe seem to be different color schemes. Okay, that didn't change. Let's change it to be 1, 3 again. Huh? Really? What? What's going on there? Am I picking values which are just luckily the same color scheme? Let's try 1, 9. Ah, yeah, there we go. Okay, so yeah, that's color. Okay, that's cool. So the first 3 bytes of the level data seem to correspond to color, the type of the block used for the plane of the level, and then the height of that plane of blocks for the level. Okay, so we'll note those findings down into the debugging notes text file. The next bytes that are read in from the code execution is 82 for 1029 memory address, and the code that reads that is here, 96AC, right? I think 96B1, 96B6, sorry. We'll note that down in the debugging notes text file as well. This is intensive debugging work going on here, stepping through the code and writing notes down on what seems to be happening. So we'll be even more methodical about this because it helps to spot patterns later on. So let's change what I think is maybe height, maybe. Is that block type? Not entirely sure. Let's change that to be 2. Ah, that's definitely height of these 3 blocks here. Okay. Let's redraw the screen. Yep, okay, that's definitely height of those 3 blocks. Okay, let's reset it back down. Okay. So what does this 8-2 signify? Well, the code, let's change it back to 3 and then make it appear really high, right? So I think that's the height of the block in these bytes here. There we go. Cause the game screen to redraw by pressing F1. That's a really handy feature in the game. By pressing F1, it redraws. Well, F1, F2, F3. No, F1, F3, F5, and F7. Right, the function keys which change the view. Well, I've corrupted the memory memory map there by changing that from. There we go. Okay, so yeah, 2 in the code was a special case. 3 is a different case, right? So the code, when it was a value of 2, anding out or masking out the 8 there, that seemed to be jumping through to a special case in the code. This last value seems to be, okay, okay, so meta tiles perhaps. Maybe it's drawing a collection of blocks, because this is not one single block in the map. Look, this is a long bridge of 4 blocks. That's 3 blocks. Okay, so I think maybe that third byte there corresponds to kind of like a meta tile index of basically, when I say meta tiles, I mean like a collection of tiles or blocks to make, which are more complicated than just single blocks or tiles on their own. Okay, so That's kind of like the height. It's definitely the height. Okay. So we're getting somewhere with how the level data is constructed. We need to do some more investigations though. So I have this collection of 2 by 2 quite high blocks here. If I change this value, no, that's the collection of 2 by 2. If I change that value there from 1 3 to 2 3, it seems to move it to a different. If I change that to 3 3, then that seems to move it to a different place. Ooh, okay, so that's the coordinate or the offset within the level map. If I've changed it to 4 3, it will be even more. So 3 is the last 3 is the height. But reading the code, it seemed to shift out the bottom 2 bits, maybe, or the bottom 3 bits, I think. And then that's the offset. Ooh, look, that's the height at that different position. So the upper 6 bits seem to correspond to the offset within the position within the map itself. Huh. Okay. Oh, so it's offset position plus height information. Well, that kind of like makes sense that it's all in the same byte, I suppose. That's quite cool. So it means that this collection of meta tiles or blocks, if you like, can be positioned within the level map data itself, within the screen itself, sorry. Okay, so this is why the game seems to have quite a large number of map screens, is that the map screen data itself seems to be quite, it seems to be painting brushes of blocks, if you like, or meta tiles of blocks into the level grid data as like a pre-calculation step. So that's why we seem to have a relatively small number of bytes for the level screens, because it's sparse. It's a sparse level data format. Because if you're drawing meta tiles and stuff like that at different positions and reusing all of this data, then you've got a sparse data format which compresses quite nicely. It compresses the level representation quite nicely, a lot better than if you had uncompressed, 8 by 8 by 8 level grid data in memory, which is 512 bytes per screen, which is quite a lot of data. So yeah, I can move these bits of data around by changing these bytes. So I've changed the level data so that it actually just contains one block, or it contains the plane of blocks on the bottom, and then it just contains one block. And I can change the block definition, and this single block definition has all of the values between, 0 to 1f, I think it was. And as long as I avoid 2, which was that special case block of code, I can have a single rotated block at any grid level position that I like. I've terminated the rest of the level data with 2 zeros, which terminates the level list, the level screen level data anyway, or the screen data. So I'm just concentrating on understanding this single block. By poking values into the memory here and then telling it to re-render the screen, I can understand better what this is doing. So yes, if I use that magic value of 2 in the block data, it then uses this special case meta tile. So I've changed the level data so it just uses this magic special case 2 block type at a height of 1 with the meta tile 17, and I get this row of 4 sloping blocks. Now if I'm stepping through the code, this code, when it does the compare with 2 in a branch not equal, it goes into this different path here. And what it does is that it seems to start searching in this, well, it reads the meta tile value here and it stores it into FD. Okay, I'm calling it the meta tile now because it's a collection of blocks. And then it seems to be stacking the current level data, or the screen level data position, the level data basically, and then it seems to be doing extra calculation. Well, it seems to be starting to read extra data by starting to scan the values of the memory table at 400 in hex. And it seems to be comparing it with the metatile index. Oh, so remember how the level data was set out? It was set out in terms of coordinate and size. This one, and then it contains the level data, and it scans through until it finds a matching coordinate before it starts processing the level screen data. This code seems to be looking for a particular metatile index value and then jumping over that number of bytes if the metatile index value doesn't match. This level structure seems to be quite intriguing. So it seems to have like an index of metatiles which are referenced by this special case block type of 2. Okay, and then it seems to be reading the metatiles from this other area of memory. And then once it finishes processing once it finishes processing the matched metatile, when it's drawing the metatile, I bet it returns back, because it was doing all of that push accumulator, which is basically stacking the values of the current level screen data position in memory. So I'm betting it's going to restore those by doing a PLA and a PLA and storing them into the relevant 0-page memory locations again. PLA is pull accumulator, which pulls the accumulator off the stack. PHA pushes the accumulator onto the stack. And it's a good way of storing temporary values. So look, yeah, that's metatile 1 with 8 bytes of metatile 1 data. Yep. And then I think it's metatile 2, and then it has A bytes of metatile 2 data. Interesting. Yeah, so the special, it's a metatile, but we'll call it a special block, right? Same thing. So it's a special block type which comes from the level screen data. That basically that third byte when it's the special case block type of 2, right? And then it has block size -2 bytes of data repeating from the second byte onwards. Okay, good. And there we go. Just above where I am at the code, it's going to execute those PLA, STA, PLA, STA, PLA, PLA, PLA. So yes, it's pulling the current level data screen position in memory for the data itself that it's decoding. It pulls it back off the stack. So actually these special kind of like metatiles can be nested quite deeply, because metatiles or metatiles can refer to other metatiles. And then it keeps on doing pushes and then pulls, and then eventually it gets back to the level data and the level screen data will then terminate by having 2 zeros at the end of the level screen data itself. Gosh, okay. So that's how the level data can actually be quite complex in this game. Is that it uses this nested arrangement of special case blocks and meta tiles, if you like, meta blocks of data which can be stacked all the way through memory and rendered at different positions. Cool. So I have this long arrangement of white blocks here. If I change that 4 to a 2, so making it 42, making it 22 from 42, and then re-render, look, this arrangement of white blocks rotates 90 degrees. So there seem to be some rotation or flip bits in here. Maybe rotation. Let's experiment a bit more. So this collection of 3 sloping blocks, if that's 22 and then change it to 42, re-render, yep, that rotates around again. Even more intriguing. Okay, so let's change that to be 0, 1, and then it moves over there. So that's the starting position. Yeah, okay. So it seems that has rotated it 180 degrees. So for putting 4 in there, 42, or rather 4, and then the special case block 2. So that seems to be mirroring it, or maybe rotating it. Let's have a little another check. So changing that from 220117, right? If I change that to be 1, 1, and re-render. Okay, that moves the position. Okay, so let's move that position back again. So this is rotation, not not mirroring. So let's update that. So the origin changes when you rotate, of course. If you're rotating it 90 or 180 degrees, then the origin point will change, right? So if I make it 60, which is a combination of 2 plus 4 bits, there we go. And then if I move, no, that's a different block, meta tile. Let's change that to be there, and then that should move across. Yeah, there we go. Move it back again to the left. Yeah, there we go. Okay, so yeah, 60 is definitely rotate 270 degrees, which is even more fantastic, right? This map level data format has the ability to rotate, probably blocks as well, but certainly the meta tiles. Excellent. So you can create some really quite complex levels with this, because you can compose the levels by drawing different meta tile blocks at different positions and different rotations. That's really quite cool. I really do like that. So that kind of explains how this game is able to squeeze in such a large variation in level maps, is by using level data or level screens composed out of rotated meta tile blocks, cool, at different positions and heights. We know the starting screen is at coordinate 4040 in hex, so let's hunt through the memory for those 2 bytes. In 0 page, they appear at 44 and 4C, or 44 and 4C in hex. So let's change 44 and 45 in hex in the memory in 0 page from 40 and 40. There we go. We changed to a different coordinate in the level map, and these map values changed. So let's change that to 0 and 40, and then redraw the screen. And there's no 0 and 40. Okay, let's change it. Now I'm constantly falling through the level. Daisy, that's not very good, is it? Or I'm constantly starting at a non-existent level map screen. Okay, there we go. Managed to reset it by changing 4C back again. Yeah, 4C and 4D are constantly being written as the player is in the map. Okay, yeah, that kind of makes sense. I think 4C and 4D are kind of like a backup copy of the last known good screen that you were on. So let's update the debugging notes text file here, if I can type correctly. There we go, map coordinates. So I think if we change those values, we can teleport to different screens. Let's change the coordinate back to 4040 again. It's not taking it because it's restoring it from 4C again. Okay, let's go back again. There we go. Okie dokie. Being able to change map coordinates is quite a useful cheat, I suppose, in this game. Anyway, I think we'll leave that video there, because I've gone through all of the things I wanted to find out. I think I've found out how this game works with respect to the map data format. And I think it would be possible to make extra map screens now in this game. The only thing I couldn't really find, and I didn't want to make this video too long, is how the enemies, lifts, and crystals are distributed through the map, but maybe that's something for an extra video. But I just really wanted to see how this game dealt with rendering a relatively complex 3D map view with so many map screens, and that's because it uses composable meta tiles based on position and rotation as well, which really helps, and also how the game was masking out its sprites. So thank you very much for watching these deep technical dive videos. If you like this kind of video, then please do consider liking or subscribing to my channel, and I really hope to catch you around next time. Have a great day, evening, or night, wherever you are.